Hello friends, it's a beautiful afternoon in Kigali, and I'd like to take the opportunity to introduce our second lesson of gravitation. This is lesson number 2 of gravitation. And as we advance, I expect that you should be now developing the concepts of gravitation. Do not forget, this is physics 9. Sorry. This is physics 9702, and this is specifically paper 4. So if you are not doing the Cambridge Physics 9702, of course, gravitation remains gravitation in whatever curriculum you are studying. But of course, this is specifically designed to meet the demands or the needs of a student doing Cambridge ASA level, and specifically who is going to sit for physics paper for advanced structured questions. Okay, so I want us to specifically start from where we stopped in the previous lesson. I think we had introduced gravitation, and we had looked at the relationship between the relationship between the force and the masses, where we saw Newton's law of universal gravitation. We also saw Kepler's third law, which was the most important law here. So from our previous lesson, you should be able to define a field, a gravitational field line. You should be able to state Newton's law of gravitation or Newton's law of universal gravitation. And you should be able to use Kepler's third law, or you should be able to prove that Newton's law of gravitation is consistent with Kepler's third law. That is, we mentioned that t squared is directly proportional to r cubed. By this point, or at this point, you should be able to prove that. So today I want us to move to something very important, and that is gravitational field strength. We have been talking about acceleration due to gravity, that is g, but we didn't know that it is sometimes, or it is correctly called, the gravitational field strength. What do we mean by gravitational field strength? Recall, we have already seen that the force due to the gravitational field will depend on the product of the masses, that is the large mass and the smallest mass. It also depends on the square of the separation between the two masses. We say the magnetic field line due to the Earth's surface was actually radial. The field lines appear to be terminating to the center. And we said for an observation taken from outside or away from the Earth's surface, the observer gets an impression as if the Earth is behaving as a point mass whose entire mass is concentrated in a small region, which is the center. So for observations outside the Earth's surface, the Earth is behaving as a point mass. But you will notice, although the field is radial, as you move away from the Earth's surface, the field lines move further apart, as you can see. As you get closer to the Earth's surface, the field lines are close to each other. What does that mean? The field strength increases when you get closer to the Earth's surface, and it decreases as you move away from the Earth's surface. To be able to determine or to define gravitational field strength, we cannot know the gravitational field strength until a certain mass placed in that field experiences a force on it due to the other large mass. So let's consider a unit test mass m placed in the gravitational field. This experiences a force which is attractive towards the Earth's surface. And remember, the force between that test mass, that is, the force between that test mass and the mass creating the field, let me say the mass creating the field is having mass capital M. You know, some people are colorblind, I need to change the color. So the force which is experienced by that test mass is going to be equal to capital G capital M small test mass divided by the square of the distance between the centers of the two masses. So this is the force experienced by this test mass. But then the gravitational field strength at this point where the test mass is actually going to depend on its distance from the center of the Earth. For example, I'm considering the Earth. So the gravitational field strength at any given point is defined as the force per unit test mass acting on a small test mass placed in the region of the gravitational field, or acting on a small test mass placed at that point. So if I want the gravitational field strength at point P, then I will determine the force acting on a unit mass placed at point P. A unit mass, when I talk about a unit mass, I mean mass of 1 kilogram, the mass of 1 kilogram. So we are defining gravitational field strength as the force acting on a unit test mass placed in a region of the gravitational field. And it is actually the larger mass which is creating a resultant gravitational field on the smaller test mass. So when we try to substitute the force here, this gives us capital G, capital M, small m, divide by r squared, then divide by this m here, and the small test mass cancels out. So we realize that the gravitational field strength is therefore given by capital G, capital M, divided by r squared. The gravitational field strength due to a small test mass is given by this expression here. But of course, since it is defined as force per unit test mass, we know that the units of gravitational field strength or acceleration due to gravity were actually initially meters per second squared, but since it is force per unit test mass, it can also be newtons per kilogram. So we are saying it's unfortunate that some of you have not studied IGCSE electric fields, but I expect that you must have studied some electric fields. Fortunately, our next unit is going to be electric fields. So in electric fields, we always imagine a unit positive charge and place it in the region of the electric field. And in a gravitational field, we are also going to imagine a unit test mass. Of course, we can't use positive or negative on masses, so I can't say a unit positive mass or a unit negative mass, not at all. So in a gravitational field, we imagine a unit test mass. Just like in an electric field, to define electric field, we shall also imagine a unit test charge, a unit positive test charge. So we have established already that the gravitational field strength at a distance from the given gravitational field is given by this. You realize, you and me, that the gravitational field strength is not actually depending on the small test mass. It is actually depending on the large mass, because an object or a small test mass moves in the direction of the resultant field. A small test mass will move in the direction of the resultant field, and the field strength also depends on the size of the mass. The Earth being massive than our test mass is creating a resultant gravitational field onto our test mass. So all the masses we come across in the lab have what we call finite sizes. They have definite sizes or specific sizes. But of course, for calculations involving gravitational force, it is fortunate that a spherical mass behaves as if it were a point mass at the center of the sphere. That's why you see the field lines are actually coming to the center. A spherical mass is assumed to behave as if it is a point mass acting with all its mass acting at the center, or where a point mass at the center of the sphere, or a point mass is placed at the center of the sphere, with all the mass of the sphere being concentrated at this point here. This is very similar to the idea that the charge on a conducting sphere can be considered to be concentrated. at the center of the sphere, as we shall see in electric fields. For now, we are saying for a spherical object, since the field is radial, its mass can be considered to be concentrated at its center. Since the field is radial, the field lines appear to be terminating to the center, meaning that the Earth is appearing as if it is pulling everything towards its center. So we can assume that the entire mass of the Earth is concentrated at its center. So the gravitational field strength will always be given by this expression here. As a student who has been established, or a student who has dealt with gravitation for some time, you will know that capital G is 6.67 times 10 power negative 11. The units, I think, they are newtons, meters squared per kilogram squared. We have also established already that the mass of the Earth, I want to try and estimate or verify the gravitational field strength on the surface of the Earth. The mass of the Earth is approximately 6.0 times 10 power 24 kilograms. By now we are aware of that value. And we are just estimating at the surface of the Earth, so we shall consider r to be the radius of the Earth. And the radius of the Earth is approximately 6.4 times 10 power 6 in meters. Let's try to estimate the gravitational field strength just on the Earth's surface, which will be 6.67 times 10 power negative 11 times m, which is 6.0 times 10 power 24, divided by r squared, 6.4 times 10 power 6, and this is squared. So I'm trying to press my calculator. You can also try to press yours. So I am actually getting a value of approximately, using these values, I'm getting a value of approximately 9.7701. This is going to be newtons per kilogram, which to two significant figures is approximately 9.8 newtons per kilogram as acceleration, the gravitational field strength on the surface of the Earth. So we are saying the force acting on a unit test mass, the force per unit test mass, the force per unit mass is what we are defining as the gravitational field strength. The force per unit mass is what we are defining as the gravitational field strength. I've already established the relationship between the gravitational field strength G and the acceleration due to gravity. How did I do this? I have considered, maybe let me use the next page again. Gravitational field strength. We have already established the relationship between the gravitational field strength and capital G, where capital G is the universal gravitational constant. We have considered a unit test mass m moving in its orbit around another large mass capital M. So we assume that capital M was the Earth and the small m is the small test mass. And we have said there is a natural force of attraction between the two masses. This force is given by Newton's law of gravitation. And this force, which is the force due to gravity, was the product of the two masses divided by the square of the separation between them. But we have defined gravitational field strength small g as the force acting on a unit test mass. Therefore, when we substitute this into this, we realize that this would be G capital MM over R squared divided by small m, and small m cancelled. So we realize that the gravitational field strength was equal to capital G capital M over R squared. This is the expression that we have already established. And this means that the gravitational field strength does not actually depend on the small test mass. The gravitational field strength does not depend on the small test mass. By the way, sometimes, since the force between the two masses is always attractive, I repeat, the force between the two masses is always attractive. Earlier on, I've already mentioned that we normally assign attractive forces negative values. So sometimes you will not be surprised to find gravitational field strength written as negative G capital M over R squared. And by the way, this is a very important thing because many times you'll find the graphs of G against R drawn below the x-axis, meaning that naturally the G is negative. G is a minus value, G is negative, or G is supposed to be naturally negative simply because the force between two masses is always attractive and we always assign attractive forces negative values. We always assign attractive forces negative values. That is a convention. A convention is a rule. From what we have established, you must have noted the following. By the way, using this expression, we considered now, we try to estimate the gravitational field strength just on the surface of the Earth, where we knew this, we knew the mass of the Earth, and we knew that, and this gave us approximately 9.8 newtons per kilogram, two significant figures. There are a few important things that you need to note. Number one, a negative sign is sometimes added following the convention that attractive forces are given negative values and repulsive forces are given positive values. That is a convention, and I'm saying convention is just a rule. Number two, the inverse square law applies to values of G. When the distance is measured from the center of the Earth, there is a little change in its value close to the Earth's surface, even when flying in an aircraft at a height of 10,000 meters. So gravitational field, we are saying that the gravitational field strength G, since it has been established as capital G M over R squared, it is following the inverse square law. In fact, because G is a constant and M is a constant, we simply say that G is inversely proportional to the square of the distance from um, the surface. When the distance is measured from the center, there is a little change in its value close to the Earth's surface. In fact, if you try to add, if the radius of the Earth is 6.4 times 10 power 6 meters, that is the distance from the center of the Earth to the surface. If you are at a height of 10,000 meters, then it means the radius of orbit or the distance from the center will simply be a 6 point, I think that will be 4 times 10 power 6 plus 10,000. You can try to add and see 6.4 exponent 6 plus 10,000. This is just going to be 6.41 times 10 power 6. You notice that this value here is approximately the same as that. What does that mean? It means that your value of G does not change significantly even when you are flying at 10,000 meters above the Earth's surface. So any distance at any value close to the Earth's surface, the value of G is almost the same. There is very little change in its value close to the Earth's surface. Number three, you must also have noticed that the equation above, that is G is equal to capital G M over R squared, depends upon the mass of the larger object and does not depend on the mass of the smaller object. So it is the equation G is equal to capital G m over r squared is depending on the larger mass. It is not depending on the mass of the smaller object. So the mass m, we saw that from the equation, it cancelled out. What does this imply? At one point, you might have been asked a question that suppose you have two objects, one very large and one very small, but dropped from the same height on the top of a building. Which of the two lands on the ground before the other? I know very fast a layman would have thought that it is actually the larger object which lands faster. Unfortunately, we realized that if two objects are above the Earth's surface, their acceleration due to gravity or the gravitational field strength at the point where they are is not depending on their mass. It is actually depending on the mass of the Earth. Therefore, the acceleration due to gravity alone is the same on all objects, independent of their mass or their size, their density, or even their speed. The gravitational field strength on two objects of different masses is actually the same because it is not depending on the mass. It does not depend on the mass, it doesn't depend on their size or their density. So somebody might be wondering, is that really very true? You can always perform this experiment, especially in a vacuum, and see if it isn't true. So, for any mass on the Earth, we infer that the acceleration due to gravity is dependent on the mass and radius of the Earth only, and G does not depend on the mass of the body we are considering. In the absence of air resistance, G acts equal for a large and small body. In that case, a small and large object, when released from the same point, will reach the Earth's surface at the same time because G is independent of their sizes or G is independent of their masses. G is only depending on the large mass, which is now the Earth, not the other two masses. So even if you are weighing 80 kilograms and another person is weighing 65 kilograms, if you fall from the same point, then the gravitational field strength is the same for both of you. If you were to fall in a vacuum or in a place in the absence of air resistance, then G acts equally for both of you because it is not depending on your masses, but it is depending on your distance from the center of the Earth and the mass of the Earth, not your two masses. So, for any mass on the Earth, we infer or we conclude that the acceleration due to gravity is dependent only on the mass and radius of the Earth. G does not depend on the mass of the body. In the absence of air resistance, G acts equal for a large and a small object. Number 5. In that case, a small and large object, when released from the same point, will each, this is supposed to be will reach the Earth's surface at the same time. Because if there is no air resistance, and you consider the equation, for example, V squared is equal to U squared plus 2AS. There is no air resistance and A is constant. Then V squared, of course, if we release them from rest, then initial velocity is 0. So it means V squared will be equal to 2AS. But remember, A is constant and the objects are going to fall through the same distance. That means the final velocity with which they reach the Earth's surface will also be the same. Then from the first equation of motion, V is equal to U plus AT. Of course, we shall always realize that the time is the same. So in that case, I'm saying a small and large object, when released from the same point, will reach the Earth's surface at the same time. Number 6. However, G may be different even when you are on the Earth's surface. Okay, so you might be wondering if G, or the gravitational field strength, is the same on all parts of the Earth's surface. Uh, it may not be exactly the same because of what we call local concentrations of mass. Local concentrations of mass in the Earth can change the magnitude of the acceleration, but this only occurs in the third significant figure. That means the first two significant figures of the value of G are approximately the same, but the last digit may slightly change. When I talk about local concentrations, there are some points of the Earth, some places of the Earth which are mountainous, are made up of dense rocks, and so on and so forth. That means the mass of the Earth is slightly more concentrated in those areas compared to other parts of the Earth. So these local concentrations, or in areas which are mountainous, G is expected to be slightly larger, but only different from that in other parts of the Earth in only the third digit, in the third significant figure, if I could put it like that. So this could make a G to be slightly different because of some parts of the Earth being made of very dense rocks, which means that the density of the Earth is not uniformly distributed. Yet earlier on we saw that every time we use Newton's law of gravitation, one, we are assuming that the masses are spherical perfect spheres. Two, we are assuming that the density is uniformly distributed. And three, we are always assuming that the masses are actually point masses. But local concentrations of mass in the Earth could change the magnitude of the acceleration of gravity, especially in the third significant figure. So, every time you go up a mountain, the value of G is actually going to get larger, yet somebody would expect it to become smaller because they are believing, or we have already established, that G is inversely proportional to R squared. But when you go up the mountain, the value of G would instead get larger instead of being smaller. This is not depending entirely on the distance because you have gone far away from sea level, but is depending on the dense rocks in the mountains. And lastly, the field strength due to the masses especially that we find in the laboratory, are very tiny. The field strengths, when I say strengths, that is plural. The field strengths due to the masses that we normally find in the laboratory are very tiny. But those that we know in space, especially objects such as the moon, the sun, other planets, the field strength that we find for such objects are extremely large and therefore cannot just be ignored. Those field strengths for large objects are also large, so we cannot easily ignore them. So I've already mentioned that G may not actually be the same everywhere. Even on the Earth's surface, G is not the same. Ignoring the concentration of rocks in different parts of the Earth, G is not going to be the same. So what factors make a G to vary? What factors make the acceleration due to gravity or the gravitational field strength to be slightly different? The acceleration due to gravity is not constant everywhere. That one we know right from the start. It actually varies from one place to another place. For instance, uh, calculations have shown that G at the equator, I'll call it G capital E, is approximately 9.78 newtons per kilogram. And yet, the same experiments have showed that G at the poles, which I'll call G at the poles, is approximately 9.83. Then the question is, why is G different at the equator from G at the poles? Your weight at the equator will not exactly be the same as your weight at the poles. There will be a very small difference. So which factors affect the value of the gravitational field strength? Note that gravitational field strength has been given as capital Gm over r squared. Note that this capital M is referring to the large mass, the large object creating the field, not the small test mass. So there are three important factors that I want us to explore. There are three important factors that I want us to explore. The first one is latitude. Geographers will tell us what we mean by latitude, but we don't want to go into the geography. So when someone talks about latitude, geographical, I think those are imaginary lines running from one end of the earth to the other end of the earth. Geographically, the earth's shape is not a perfect sphere. Yet, every time we use this expression, we are assuming a spherical object. The earth's shape is not a perfect sphere. In fact, the equatorial radius, which I will call RE, meaning equatorial radius, not radius of the earth. The equatorial radius is greater than the polar radius, which I'll call RP. The equatorial radius exceeds the polar radius. What do I mean by that? Geographically, the Earth bulges at the equator as it flattens at the poles. That means the distance from the center of the Earth to the equator is greater than the distance from the center of the Earth to the poles. That's what I mean by the equatorial radius being greater than the polar radius. Earlier on, we have established that acceleration due to gravity is depending on this distance. If the equatorial radius is greater than the polar radius, that means G at the equator is going to be G mass of the Earth over the radius of the equator. And G at the poles is going to be equal to capital G mass of the Earth over the radius of the pole, radius to the pole, or distance to the pole from the center. Note that the equatorial radius is greater than the polar radius as a mathematician. Or mathematically, therefore, if RE is greater than RP and yet G is inversely proportional to this square, you will notice that G on the earth, on the equator, at the equator is going to be less than G at the poles. So we are saying the value of G could slightly be different because the earth's shape is not a perfect sphere. The earth's shape is actually elliptical. Some places are far away from the center of the earth, while others are near to the center of the earth. So we are saying the earth's shape is not a perfect sphere. The equatorial radius exceeds the polar radius, which makes G at the equator less than G at the poles. Take for instance, or let's see a simple example. If the radius of the Earth at the equator is 6371 kilometers and at the poles is 6350 kilometers, determine the weight of a man who has a mass of 60 kilograms. So we have been given the equatorial radius and the polar radius, and we want to find the weight. Weight is equal to mass times G. All we need is to find G. G at the equator is going to be equal to, we are going to consider the mass of the Earth, which is going to be, of course, this is capital G, capital M over R squared. Simple substitution. 6.67 times 10 power negative 11, that's capital G. Mass of the Earth, 6.0 times 10 power 24. R squared, this would be 6,371,000 squared. That is G on at the equator. Let's find G at the equator. 6.67 exponent negative 11, 6.0 exponent 24 divide by 6,371,000 squared. So I am finding G at the equator to be approximately, by considering these values here, I'm finding G at the equator to be approximately 9.85, actually 86, using these values. Let's find G at the poles. G at the poles will simply be 6.67 times 10 power negative 11, 6.0 times 10 power 24 divided by 635,000 squared. So this is 635,000 squared. So this is giving me 9.92 as the value of G at the poles. So we try to find the difference in the value we try to find the weight. So the weight at the equator will be 60 times 9.86, and the weight at the poles will be 60 times 9.92. Calculator, 60 times 9.86. So this weight is going to be 591.6. 60 times 9.92, and this is 595.2 newtons. So there's a difference, a small difference in the weights of the two. Okay, so the other factor that I want to talk about, the other two factors which I want to talk about, which cause the value of acceleration due to gravity or gravitational field strength to be different, we have the rotation of the Earth. We know that the Earth spins west to east about its axis. The rotation of the Earth about its axis brings about what we call centripetal force. And note that if an object is at a given altitude or at an angle above the equator, then it means the centripetal force is not acting towards the center of the Earth. Note that the Earth is spinning about its axis, and therefore it is spinning together with this object. So if this object is at an angle above the equator, or it's at an angle away from, how they call it, I think that is altitude, then it means as the Earth spins, the object also spins in a circular disk whose center is along the poles, but not at the center of the Earth. So the rotation of the Earth also causes G to vary. Maybe look at it in details. Let's see how does the rotation of the Earth affect the value of G. But all we know is that as the Earth spins, any object at a certain height or at any angle away from the equator, or at a distance or at a height from the equator, is going to also be spinning. And as it spins, its center of spinning with the Earth will be just towards, or it will be at or along the poles. So the object will spin through a circular disk. So let's assume there's an object here at this point. And if the Earth spins about its axis, north and south, then this object also spins in a circular disk whose radius is now small r, with its center just at the poles. So the object spins together with the Earth, but its centripetal force is not directed towards the center of the Earth. Instead, the centripetal force is towards this center here. That means the centripetal force has a component along the direction towards the center of the Earth. The centripetal force has has a component along the direction towards the center of the Earth. If we want, we can establish the centripetal acceleration. Remember, from centripetal force F is equal to mv squared over r, where v squared over r was centripetal acceleration. I'll just consider centripetal acceleration for now. So centripetal acceleration is going to be v squared over r. Is v squared over r. Remember, from circular motion, v was omega times r, which was 2 pi over t, then times r. So it means the centripetal acceleration, I'll write here, the centripetal acceleration A is going to be equal to, that will be v squared, which is 2 pi r over t, but this is squared, and I divide this by r. This gives me 4 pi squared r squared over t times r. So one r has cancelled. So the centripetal acceleration is going to be 4 pi squared r over t. That is the centripetal acceleration. But what is r? We can find the component of r along this direction here. What is small r in terms of this? If I resolve this horizontally, I want to resolve small r along this direction here. If this angle is theta and this is theta, resolving this along this, I think that is cos. So it means r, small r is the same as capital R cos theta. So this will be capital R cos 30. So it means the centripetal acceleration SC will be equal to 4 pi squared times small r is capital R cos 30 divided by t. So if I know the radius of the Earth, if we know the radius of the Earth, for example, r is around 6.4 times 10 power 6 meters, then we can say that the centripetal acceleration is going to be equal to 4 pi, I will just substitute 4 pi squared over t, 24 times 3,600. So the period of the Earth, that is 24. So I will say 24 times 3,600. But this is squared times r, which is 6.4 times 10 power 6 cos of 30. So shift 4 pi squared divided by the answer times 6.4 exponent 6 times cos of 30. So I'm obtaining the centripetal acceleration as 0.03 meters per second squared. So it means this centripetal acceleration affects the acceleration due to gravity. So if I take this one further, it means there is a centripetal acceleration which reduces. This is the centripetal acceleration along this direction here. So that means this affects the acceleration due to gravity. So the actual acceleration due to gravity for this object at this point here, if I call this point A, the actual acceleration due to gravity at point A will therefore be the acceleration due to gravity if the Earth was to be considered stationary compared to the acceleration due to gravity since the Earth is spinning. If the Earth was to be stationary, I think the acceleration due to gravity is approximately, let us check. For a stationary Earth, what is the acceleration due to gravity? If the Earth was stationary, the acceleration due to gravity would be equal to 6.67 times 10 power negative 11 times the mass of the Earth, which is 6.0 times 10 power 24, then divide by the radius of the Earth, which is 6.4 times 10 power 6, and this is squared. Let's find this. 6.67 exponent negative 11, 6.0 exponent 24, 6.4 exponent 6, but this is squared. So this, if the Earth was to be stationary, G would be approximately 9.77 at that point. But since the Earth is spinning, then G at that point A is going to be approximately 9.77 minus 0.03. And this would give us approximately 9.74 newtons per kilogram or meters per second squared. But of course, you are going to notice that this difference only exists in the third significant figure. The difference will only be appreciable in the third significant figure. Therefore, the acceleration due to gravity also slightly changes, but this is only happening in the third significant figure. On average, we take the acceleration due to gravity to be almost the same, whether the Earth is spinning or it is at rest. The third factor that we talked about, which causes or which could be responsible for the variation of the acceleration due to gravity, is altitude and depth. Altitude and depth. How does altitude and depth affect acceleration due to gravity? Is the acceleration due to gravity as we move away from the Earth's surface behaving the same way as the acceleration due to gravity when you go inside the Earth's surface? Let's verify. Let's consider a mass moved away from the Earth's surface, and we shall also consider the same mass brought deep into the Earth's surface. Does the value of G behave the same way outside and inside the Earth's surface? Maybe yes. Let's verify. So another factor which affects the value of acceleration due to gravity or gravitational field strength is its altitude or depth. I think altitude is the height above sea level. How far is a given mass from the Earth's surface? That also affects the value of G. But I mentioned for G to be significantly affected, the object must be far, far away from the Earth's surface. For a small height above the Earth's surface, G is almost constant, because for a small height above the Earth's surface, when I add the height to the radius of the Earth, it is approximately the same as the radius of the Earth. So when somebody says just above the Earth's surface, is actually literally referring to the radius of the Earth. Because for a small height above the Earth's surface, when I add that height to the radius of the Earth, it is approximately the same as the radius of the Earth. So let's consider a body of mass small m. Let's consider a body of mass small m. Initially, we shall consider it when it is on the Earth's surface. M is just on the Earth's surface at E, at point E, just on the Earth's surface. Of course, this experiences a force which is equivalent to the weight of the object. Let capital M be the mass of the Earth. Capital M is going to be the mass of the Earth, the entire Earth. When you are just on the surface, capital M is going to be the mass of the Earth. We are going to assume that the entire mass of the Earth is concentrated at its center. So the weight of the object at E, the weight of the object is equal to mass times gravity. That is the weight of the object. But we have already established that gravity, so this will be mass times capital G, capital M of the Earth over, I'll call that one RE squared, the radius of the Earth. That means G on the Earth's surface is capital GME divided by RE squared. Note that capital GME is a constant. So G on the Earth's surface is a constant because the radius of the Earth is a constant. Capital G is a constant. The mass of the Earth is a constant. On average, we take it to be approximately 9.81. Let's now try to move the object far away from the Earth's surface. I will divide this for simplicity. Let me divide this into several parts. So let's now take the object far away from the Earth's surface. Now we are taking the object at point B. Note that the radius of orbit this time, or the distance from the center of the Earth, is greater than the radius of the Earth. What happens to G as you move away from the Earth's surface? That is now our challenge. Note that R is equal to the radius of the Earth plus its height h from the Earth's surface. Let us assume that h is significantly large. Let's assume that h is significantly large. So G at point B is going to be equal to capital G, capital M divided by the square R of the distance from the center of the Earth. But note that R is greater than RE. So if we want to establish a correct relationship, let's divide the two equations. Let this be equation number 2. So let us divide. G at point B divided by G at point E is going to be equal to capital GM over R squared times, I get the reciprocal because I'm dividing, RE squared over GME. By the way, this is ME, mass of the Earth. Mass of the Earth. So this constant has cancelled. So do you notice that G at point B is going to be equal to RE squared over R squared times G on the Earth's surface. Note that G on the Earth's surface is constant and the radius of the Earth is also constant. You don't need to be a genius to observe that G at point B is inversely proportional to the square of the distance from the Earth's surface. So G varies as the inverse square when you move away from the Earth's surface. G decreases. G is inversely proportional to the square of the distance from the center as you move away from the Earth's surface. For any point above or outside the Earth's surface, the acceleration due to gravity, the gravitational field strength, varies inversely as the square of the distance from the center of the Earth. On the other hand, let's try to take the body into the Earth's surface. If the body is moving deep into the Earth's surface, how does G vary? How does the acceleration due to gravity behave? Does it also decrease? Let's try to verify. So this time, instead of taking the object or the mass small m away from the Earth's surface, we are now going to take small m inside the Earth at point D. So now we are here at point D. We are bringing our mass at point D. It does not require to be a genius to see that when you are at point D, there is some mass of the Earth which is not providing a force on you towards the center of the Earth. This part here is above you, therefore it is not providing a force. It's not providing a field on you towards the center of the Earth. What has happened therefore? It's like the mass which is creating the field has reduced. So I'll call the mass, the new mass of the Earth creating the field, I'll call it capital M. And you notice that capital M is less than the original mass of the Earth because not all the mass of the Earth is still providing the gravitational field. By the way, remember we always assumed the density is uniform. So if the density is uniform, then we can use the concepts of density to arrive at a simple relationship. We know that mass is given by density times volume. The mass which remains when you go inside the Earth that provides a field on you, or that provides a field on the mass, will therefore be equal to the volume that remains, which will be 4/3 pi r cubed. That is the volume. So let r be now the distance from the center to D, not the distance from the center to B as before. Then this is going to be times the density. Remember the mass of the Earth, capital ME, initially was also 4/3 pi, but this was radius of the Earth cubed. Then times the density, because the density remains the same even if you go under the Earth's surface. So we have these two expressions here. But if we consider the Earth's surface, we have already seen that at the Earth's surface, G on the Earth's surface was actually equal to capital G ME divided by RE squared. Now we want to find G at point D, which will be capital G, capital M, now the new mass, divided by R squared, which R is the distance from the center to point D. So let's try to divide these two equations. G at point D divided by G on the Earth's surface. This will be equal to G capital M over R squared times, I get the reciprocal, RE squared divided by GME. So G has cancelled. So G at point D over G at point E on the surface of the Earth is equal to capital M over ME times the radius of the Earth squared divided by R squared. So we need M over ME, and we have M here, we have ME there. Let's substitute. So I have that G at point D over G on the Earth's surface is going to be M over ME. I'm dividing these two equations. You notice that when I divide M over ME, 4/3 pi disappears, rho also disappears. So I remain with only R cubed over RE cubed. That is M over ME. Then times, this is now RE squared over R cubed. I mean R squared, I'm just multiplying by this. So when you simplify, notice that this square cancels this one, this square cancels that one. So you remain with G at point D over G at point E is equal to R over RE. So G at point D is equal to R over RE times G on the surface of the Earth. Note that G on the Earth's surface is approximately constant. Radius of the Earth is approximately constant. So it means this G over R is constant. So G at point D is directly proportional to R. What does that imply? Although outside the Earth's surface, g varies as the inverse square, inside the Earth's surface, g is directly proportional to the distance. So when you move towards the center of the Earth, g tends towards 0. When you move towards the surface of the Earth from the center, g increases to a maximum value at the surface. When you move away from the Earth's surface, again g decreases as the inverse square. I don't know whether I've tried my level best to make this quite understandable, but it should be understandable. It must be understandable. Okay, so we have now come up with two conclusions. Inside the Earth's surface, g is directly proportional to the distance from the center. Outside the Earth's surface, g varies as an inverse square. So you notice that this is a straight line. This one is a straight line and this is a curve, which is exponential towards the x-axis. Because when r is as r increases, g decreases. When g is when r is 0, anything divided by 0 is actually infinite. But I don't want to go into that. I want to begin with the Earth's surface because here the Earth's surface is actually known. So we come up with a simple graph, and this graph is a graph of g, a graph showing how g varies inside and outside the Earth's surface. Remember, inside, g is directly proportional. G is directly proportional to distance from the center. Outside, g varies as the inverse square of the distance from the surface. So we can sketch a simple graph which looks like this. So as you move towards the center of the Earth, g tends towards 0. On the surface of the Earth, g is approximately 9.81. But as you move away from the Earth's surface, g varies as the inverse square. G varies as the inverse square. I want to remind you that although this graph has been sketched with these values above the x-axis, many times you will see the graphs below the x-axis because g is equal to negative capital Gm over r squared. Note that I said negative normally indicates that the force between the masses is always attractive. Do not get surprised to see that most graphs will be below the x-axis. Actually, the correct way to draw these graphs, if this is the Earth, where this is the radius of the Earth, the most appropriate way to draw this graph would be something like this, where outside the Earth it will be like that, and inside the Earth's surface it will be a straight line here. Can't I draw a straight line? I think I can draw a straight line. Okay, so it's hard for me to draw a straight line, but inside it is a straight line because g varies as the inverse square, and outside, g varies inside, g is directly proportional to r, and outside g is inversely proportional to the square of r. So outside should be a curve turning to the x-axis. Of course, this value here on the x-axis on the Earth's surface is approximately negative 9.81. At the center of the Earth, G is 0. But as we move out towards the surface of the Earth, G increases up to a certain maximum value. And as we move out from the Earth's surface, it now decreases. So that will be the graph of G against against distance from the center of the Earth. And you should be able to draw and interpret such graphs. Okay, let's do a few examples. We can do a few examples. Examples number 1. Example number 1. The radius of the Earth is 6.4 times 10 power 6, and the gravitational field strength at its surface is 9.8 newtons per kilogram. Assuming that the field is radial, that means G is equal to capital G m over r squared can work. Calculate the mass of the Earth. Calculate the mass of the Earth. In our solution, gravitational field strength is equal to capital G m over r squared. So 9.8 is equal to 6.67 times 10 power negative 11 times the mass m divided by 6.4 times 10 power 6. Press the calculator to find m. Just cross multiply and divide. So the mass m is going to be equal to 6.0 times 10 power 24 kilograms. That is A. Then B, the radius of the moon's orbit about the Earth is 3.8 times 10 power 8 meters. Calculate the strength of the Earth's gravitational field at this distance. Strength of the Earth's gravitational field at this distance. So we want G. So gravitational field strength is equal to capital Gm over r squared. This is going to be 6.67 times 10 power negative 11 times the mass of the Earth, 6, because the Earth is more massive than the moon, so it's the mass of the Earth which is creating the field. So this will be 6.0 times 10 power 24 divided by the square of the distance between the Earth and the center of the Earth and the moon, 3.8 times 10 power 8, but this should be squared. By the way, this was squared. And when I press my calculator, pressing my calculator is giving me approximately 2.8 times 10 power negative 3 newtons per kilogram or meters per second. Then C, the mass of the moon is this. Calculate the gravitational attraction between the Earth and the moon. Since we know the mass of the moon, of course they want the gravitational attraction, that is a force. So force is equal to G m over r squared. 6.67 times 10 power negative 11, 6.0 times 10 power 24 times 7.4 times 10 power 22 divided by R. Calculate the gravitational attraction between the Earth and the Moon. In the previous example, they have given us the distance, so I will just say 3.8 times 10 power 8 squared. So let's try to press our calculator. Okay, so pressing my calculator. Pressing the calculator. This is 2.1 times 10 power 20 newtons. Example number next. The Earth has a radius of 6,400. The gravitational field strength on the Earth's surface is this. Use the information to determine the mass of the Earth and its mean density. I think that one is easy. It is similar to the first one that we have just done. Gravitational field strength is equal to capital G M over R squared. Divide by the radius 6400. It is in kilometers. I multiply by 1,000. This should be squared. So this means the mass, actually I'm finding my mass as 6.0 times 10 power 24 kilograms. Number 3. So, but they said its mean density, we can find density. Let's find density. I think density is mass over volume. The volume is volume of a sphere, so the 3 goes up, the 4 remains down, so it will become 3m over 4 pi r cubed. Okay, so we substitute. This will be 3 times 6.0 times 10 power 24 divided by 4 pi times the radius cubed. This is r cubed. R is the radius of the Earth is given as 6,000. We multiply by 1,000, but this is to power 3. Press the calculator. So this is approximately 5460 kilograms per meters cubed. That is the density of the Earth, approximately 500 kilograms per meters cubed. Number 3, treating the Earth as a perfect sphere, show that the field strength at the Earth's surface is 9.8. I think that one is easy. We have already done it. G is equal to capital G M over R squared. 6.67 times 10 power negative 11. The mass of the Earth 6.0 times 10 power 24 divided by the radius of the Earth, which is 6.4 times 10 power 6. And this should be squared. When I press my calculator, I think I've already pressed this. It gives me 9.77, approximate 9.8 newtons per kilogram. Number 4. So this was number 2. Number 3. Number 4, what is the strength of the gravitational field due to you at a distance equal to the radius of the Earth? What is the gravitational field strength due to you at a distance equal to the radius of the Earth? So let's find number 4 now. The gravitational field strength due to you, that means your mass is the one creating the field. So remember, gravitational field strength is equal to Gm over r squared. M is the mass creating the field. This time it is due to you, that means it is your mass creating the field. So this would be 6.67 times 10 power negative 11. Let me estimate the mass of a person as 70. You can also estimate yours. Divide by 6.4 times 10 power 6 squared. So this is 1.1 times 10 power negative 2 newtons per kilogram. So I want you to look at this value here. That is the gravitational field strength due to you on the Earth's surface. Due to you on the Earth. While this is very small, it is not zero. Although it is small, it's not zero. And of course, this shows that the gravitational force falls off quickly with the distance, but it is always there. It is always acting at an infinite range, or it is infinite in range. You will also realize that if we calculate the weight of the Earth on you, you will get the same answer as your weight on the Earth, using this value of the gravitational field strength. Number 5. In view of your answers to the 2 questions, I think since it has started raining, I will pause at this point. Let us start with this example next time.